Most seats are relatively flat. So that's how we're going to start, is relatively flat. We want to angle it ever so slightly so that you're chilling in your chair, right? You get a little bit of angle on that. So if I'm going to be facing left to right, I'm going to put a little bit of angle on that line. So it's just ever so slightly going up to the right. Well, that's only 2 parts of my chair. Okay? A chair needs 4 points, right? So you can support your 2-dimensional, at least, butt. So we need another 2 points. And those will need to be parallel to those. So I'll go underneath it, and I'm going to draw roughly the same length line, but staggered off of it. That's step 1. So now what I want to do is move to step 2. Pick the left or the right side. I'm not going to ask that question again. We're going to draw roughly kind of through halfway through our chair. We're going to now look to the left or the right side. I'm going to say left because that's what I started with. I'm going to look at those 2 lines. Which line is shorter? The top one or the bottom one on the left side? The top one. Since it's the top one, I'm going to start my next line there, on my next bond, and because it's the top, I'm going to go up. Okay? I could go straight up, but that's going to look ugly later. So what I'm going to do is, again, angle it. Okay? Nice way to think about it, I'm angling it with a 109.5 degree angle. Okay? I'll go through to the other side and do the same thing. When I go over to the other side, which line is shorter? The bottom. Since it's the bottom, I'm going to draw it down. Same idea. Okay? And ideally, these are all the same length, but sometimes they'll look like that, sometimes they won't. Step 3, complete the triangle out. Since it's all color-coded, we'll try and throw in orange. I don't think you'll be able to see it. Okay. And you now have a chair that faces to the right. What if we wanted to face to the left? Same idea. I will draw my mostly flat line angled to the left. Same deal through. Back to my red. Angle up. Angle down. Oh, I staggered it off-centered the wrong way. So that's one thing you'll also find, is that you'll find you're better at drawing one direction than the other. We need to stagger the opposite direction that I had staggered before. Up, down. Thank you for pointing that out. Down, down. And we now have a chair facing the opposite direction. Okay? To give you an idea, your head is sitting up there. You got a very tiny head. Okay? There's your back. Here's kind of your hips or your legs. There's your knees. Chilling out here, right? Another leg. Okay? Sitting here with your little hands. Okay? So think kind of a chillax lounge chair sofa thing. Okay? So the next part of this is referencing where all these atoms are located. Okay? When we dealt with Vesper models, oh, that sucks. It screwed up the recording. So I should go yell at whoever called me. Or stop the forwarding. We need to make sure we're aware of where everything is located. So number 1, this is where I'm going to put my head. Okay? Sometimes you'll hear me refer to it head. Sometimes you'll hear me refer to it as back. This other atom down at the opposite corner is where we put my feet. Pretty consistent on that. When we think back to Vesper models, a solid line meant what? It was a connection, but it's in the plane. Okay, so if I'm looking at this, come on, hands. Oh, we can even sort of, yeah, look at that. Look at the shadows and everything. Oof, there it is. Okay. We've got our chair facing that way. How many of those atoms are in the same plane? Which plane is a good question to ask. Okay. How about the plane we're drawing in? 2 atoms, the one I'm holding on to and the one directly opposite it. Those happen to be the atoms I've circled in black. What about the 2 atoms down here? Those are coming out towards you. Okay. So the now blue side of this is coming out of the plane. Or out plane, why not? So we could show those all as wedged. That gets a bit tedious. The orange side of it is now behind the plane. And for those of you saying this is nonsense, well, I don't need to know this. Depends. Okay? It depends on how you draw your answers. It is very common for a student to do a manipulation of this structure, and instead of doing just a rotation, does 4 rotations. Okay? Because they don't understand which atoms are in the plane and which atoms are not. To convert between this chair facing to the left and the chair facing to the right, what happened? Where's my feet in my new chair? Monday should be able to cheat a little bit on this. Your feet are now right there. That was your old feet. Where's your head? This is now your old head. Or back.
That's only if you rotate.
There is, and that's the next big thing. There is no rotation of the model. All that happened was I took the atom that was my feet and I pulled it straight up. I took the atom that was my head and I pulled it straight down. Those atoms never move out of the plane of the paper. They stay in the plane of the paper. There is no rotation of the molecule. And you're looking at it but saying, no, it had to, because the one furthest to the right here, okay, should mean it's here. No. What we're talking about here is the chair flip. Do not get confused with the location of where those atoms are. The only reason I suggest that is that if I ask you to do a chair flip with a couple extra little pieces on it, you might end up finding out that you end up drawing the wrong structure. You would draw a different stereoisomer than what I asked you to draw, which then technically means you're wrong. Right? So you have to be very careful with these flips and rotations to make sure that you are drawing exactly what is asked for and not a slight rotation off of it. Okay? There was no rotation made in this molecule. I'm going to steal that from you again. So if we start with our chair again, what happened to move? I'm now looking at the other confirmation. I did not rotate this. It is merely held in the exact same plane. Okay. The molecule does not rotate. Bonds pivot, okay, or rotate, but the molecule itself does not change its orientation. Critical observation and very difficult to see. I hate grading this section.
So then the out of plane and the behind the plane would stay.
Are the exact same.
So we don't get to use like something like this on the test.
You are allowed to use a model kit on the exam. Yes, absolutely. And I would highly encourage you to do so. As a very good model kit to build for the exam, because it's probably going to suck to have to build it on the fly, build methyl cyclohexane. If you have a methyl cyclohexane with a couple other different colored balls attached, you can answer any question relatively quickly by just moving some balls around. Okay, just like life.
Can we bring the cyclohexane?
You can bring it entirely built. Yep, in fact, that's what I would encourage you to do. So, which type of drawing allowed us to see the energy? The chair says nothing about energy. Okay? It's kind of a misleading question because we just talked about an overhead view and then we talked about a side view being the chair. Okay? Neither of them tell us anything about energy. If there's a question about energy, it is specifically referencing the Newman projection. Okay? Which then becomes confusing. When we looked at the Newman projection before, I'm going to break your model, we had at most 4 atoms. So, oh, there's a Newman projection where I'm now in the anti-conformation because my 2 big groups are opposite sides of each other. If I now go back to making a cyclohexane, Thank you for showing up prepared, by the way. Better than I could do. Okay. Where am I looking? In a Newman projection, I have to look down a bond. Which bond? As soon as I look down one, all the other ones are off skew. There are two Newman projections. That's where I'm holding my index finger and my thumb. Okay. For those of you who can't see it, it's because the other bonds aren't drawn or put on there yet. Okay. What you would end up seeing, please say, I don't have to draw it. Please, please, yes. Okay. We are now sighting our molecule. Two eyeballs because you're looking down two axes. Those bonds will now disappear. This carbon that is closest to the eyes is located where? Okay. Below the seat. Which means when I go to the Newman projection, that atom is not part of the Newman projection. It's coming off of it below. See it? Okay. The Newman projection brings in an interesting point. What happens, or what is the difference between, say, this hydrogen and this hydrogen? Actually, let's switch that up, not even those two. This hydrogen. Do they see the same thing? What is around them? This one up here looks in and it sees a ring. What does this one see? Nothing. Those two hydrogens are at different energy levels. For this molecule, does it matter? What happens if you do a chair flip? We end up exchanging those positions. They end up seeing roughly the same thing. Okay? So for this molecule, at any thermal energy, I can do the sigma bond rotations. I don't see a difference between those chairs. But what happens if instead of it being a hydrogen, I made it something else, say like a methyl group? Is that now going to change my energy? Yes. The short answer of it, this position is higher in energy than if I had had the methyl group in the other position. Why? We have an anti-conformation versus a gauche. Okay? For those of you in the Monday lab, I'm sorry I didn't tell you the answer right away. For those of you in the Wednesday lab, you might remember this. Okay? For those of you in both situations, we have our Newman projection here, where we're looking down. Right? So the relationship between these two atoms is anti. They're on opposite sides of that Newman projection bond. So we'd say there's one anti-interaction. Is there another Newman projection? I just look down this bond.
The other bond.
Is there another anti-interaction? Yes. Every time you have a substituent, there are two directions in which you need to be looking to evaluate your Newman projections. Is this important? Try the homework. Okay. So you have to be aware that when you look even at the Newman projection, you're now only looking down one axis. There's another axis you can look down, another Newman projection that you have to evaluate. These two structures, our red and blue, are technically different energies. What do we do with things that are different energies? We name them. So the red one gets referred to as the Monday. In the Newman projection, true, it's gauche. But if I put the methyl group at that position,
Oh, it's axial.
it is referred to as axial with respect to the ring. The blue one is referred to as equatorial.
But the same goes for when they were hydrogens before, when they were just hydrogen.
The same goes for when they were hydrogens. You can reference those positions as axial and equatorial. Typically we ignore hydrogens because they're pretty much always there. There's nothing we're going to do about the hydrogens. So when we start to care is when does it become something other than hydrogen? Why do we start to care then? What's the difference between hydrogen and any other element we could have put on it? The what?
You have to list them.
Yeah, we'd have to list them. But why do we care? Electronegativity is not a bad idea, but it's actually not super important here. It's electronegativity or potential for interactions because of the size. Hydrogen is the smallest atom we can put on our structure. It has to be there. Okay? If I put any other atom there, what happens? It gets bigger, which now changes the electron clouds, which now changes the space needed for that individual group. That's going to change the interactions and how the molecule flips and folds on itself. Okay? So, we've got our axial and equatorial positions. As we just very quickly addressed, our equatorials, labeled as E, give us an anti-relationship. Our axials will give us a Gauss relationship. This means, given a structure, a cyclohexane, I want to put my largest group, anything other than hydrogen, into which conformation? Into the equatorial position, because that gets me the anti-Newman projection. For those of you like, why do we have anti and axial, both starting with A and both reasonably short? I don't know. That's the way it works. Deal with it. Okay? So from here forth, you pretty much look at a structure and say, if I'm going to look at a Newman projection or a chair, I want to make sure my large group is drawn in the equatorial position. Okay? Those are all the fun conclusions. We go through and draw all that. What happens if we chair flip? Okay. How do we know we did a chair flip? In this chair, this again goes probably back to the Monday lab. In this chair, where would you be facing? You're facing the other side of this board. This is where you would put your head. It's the up portion. This atom down here is your feet portion. So you're facing through the board. When we go through the ring flip, we take our head and we turn it into feet. So we grab a hold of that carbon and we pull it down. At the same time, our feet, we need to push up and make our head. Take a look at what happened. Okay. Again, no rotations, okay, of the molecule. All we're doing is pulling the atom down. We have to notice that we do get a pivot in the bonds. Okay? And don't get semantical on me by calling that a rotation. Let's stick with pivot. Okay? So we're pivoting in those bonds. The red atom was equatorial. Now it's axial. Okay? Well, how could I tell the difference between axial and equatorial? By looking at the structure. Our axials, I have no idea why I've remembered it as this. Our axials are on the up-down axis. Maybe that's why, because I say axis. Okay? Which means, in our first drawing, that A is in the up-down axis. It is axial. What about the other one, our E? That's not on our up-down axis. So it's the other one, equatorial. What happens when we do the chair flip? What was our E is now on the up-down axis. It has become axial. Okay, what happened to our A atom? Rotates off of our up-down axis, and we have our equatorial position now. Okay? So as we do chair flips, we can exchange our groups between axial and equatorial locations. For those of you having an insanely hard time seeing this, I agree. It is really hard to see it. How many of you pulled out a model kit to actually deal with this? Half the class in Monday. And maybe they're like, yeah, I kind of get this. The other half, you're like, what the hell is he talking about? It's because you don't have a model kit in front of you. Okay? This is where the model kits come in really, really handy. Yes?
Can we apply axial and equatorial to pentane?
To a cyclopentane?
Cyclopentane?
Ish. It doesn't apply as well. But you can do the same kind of concept
Because we always have those ones that are dark down.
Yeah. Okay. Ooh. That was a bad statement to make down there. Where's that typo? Largest groups belong in the equatorial position. Why equatorial? They generate the anti-Newman projection. Okay. Questions? Okay. I think where we go with this, yay, some examples. Good way to finish it out. Let's see. Yeah, it's a good way to finish it out. So we won't quite finish it out with those examples. We'll look at some other projections because these are kind of minor contributors. For cyclohexane, we've got our two-dimensional overhead view, which you can reference with ups and downs. So we can specify our groups as wedges and dashes off of our ring. We've got these sort of three-dimensional side view that gets us our chairs. We have a three-dimensional end view that gets us our Newman projections. Okay? Those are our standard ones that we'll be working with this semester. Okay? You will likely see one question pop up for sure in biochemistry if you have to take biochem. It'll also show up probably on the final, is a Haworth projection or a Haworth. I'm not sure which way to pronounce it. It is a two-dimensional side view. I don't really know how to describe that other than that. It's really kind of weird. We're taking our overhead view that we said is two-dimensional, and we're saying all those atoms are in a plane, which they aren't, and we're turning it on its side, and now we're looking at where the groups are. Okay? So you might see that representation pop up as well. You're kind of responsible for it. You're just taking the two-dimensional, turning it on its side. That's it. Where it becomes really fun, anybody recognize that? I think it's glucose.
Yeah.
Okay. Or wait, no. What's the other one? Sucrose, thank you, that's the one. Sucrose, because it's a glucose and a fructose. Okay. Lots of fun oses. Thank you, biochemistry nomenclature system. Okay. What are we looking at here? A Haworth projection. Why did we invent Haworth projections? Every single one of those atoms has this up-down relationship. Can you imagine trying to draw this like a chair? Okay. Or like a Newman projection? It's a freaking nightmare. Okay. So we convert into the Haworth to make that a little bit easier to deal with. Okay. So general topics for your review, just a quick thing. We've got our energy strain with numbers. I'm not a big fan of numbers. Everything we've talked about, we've kind of approximated and said butane is not stable because cyclobutane, because we got a 90-degree angle and it wants to be 109.5. Your textbook will quantify it. Other instructors will quantify it. I think it's nonsense. That's not quite true. Okay. Cycloalkanes, looking at the prop, but, and pent shapes. What are the kind of relationships within those? It's important to look at, not all that big a deal for me to talk about. Okay. Models dealing with constitutional isomers. Constitutional is the same thing as structural. Okay. It just depends on who taught you. The other thing that will pop up is you'll see this IHD. Okay. It's called the index of refraction. Okay. Here's the IHD formula. Any guesses why we don't talk about it? It has too much to do with numbers. Is it helpful? Yes. When we move into spectroscopy, we'll talk about it again. Doesn't mean I like it. In fact, it still means I don't like it. Okay? And it can be useful. The reason why I don't like it, you have to have this formula memorized to use it. I have never memorized it. I derive it every single time somebody asks me about it. Literally every single time. So please don't ask me about it because I don't like deriving it. Okay? So 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of heteroatoms other than nitrogen minus the number of hydrogens divided by 2 gets you your index of hydrogen deficiency. Okay? That index can be used to predict something about the structure. For every degree of index, so every one value, you have a ring or a pi bond. So you can get some structural information by looking at it. Or you just draw the structures and realize you need a ring or a pi bond. So I can do a bunch of calculations to come to the exact same conclusion if I don't do the calculations. Okay? So we got kind of our key there. Not a bad idea to read through it just so you get a feel for it. Okay? And again, we'll talk about it in a little bit more detail when we look at spectroscopy. Okay? Which means Chapter 5 entirely off of the exam. I won't ask any questions coming from Chapter 5. I'll push the entire homework due date back to Exam 2. Okay? Chapter 5 is all sorts of fun spatial awareness stuff. Okay? So, let's go back up to these practice. Work some of these examples. These questions, I've given you some general skeletons to work with. This type of question is a super popular question because it asks two things. Number one, lowest energy. Do you understand what's going on with chairs? Okay. Officially, it's asking about Newman projections. You'll notice I didn't draw a Newman projection. Why? Because the chair, once we've looked at the Newman projection, we can just say that's our answer. And that answer being, put the largest group equatorial. Once you've got that, you don't need to look at the Newman projections anymore. Okay. The next part of this question that makes it even more dicey. What do you mean cis and trans? It's part of it.
How do you know which way?
It's nomenclature. This asks, do you understand what's going on with chairs and their energies? And do you know how to name the compound? Okay. Be very careful when answering this question. The gut instinct for most students to go through and do is to say, well, if I want it to be equatorial, so let's take a look at our chairs. These are all the same. I'm going to do the 1, 2, 1. I'm going to say equatorial and equatorial. Did I draw the cis 1,2 dimethyl? No. I drew the trans. How do you know? Which direction is that line pointing? Down. Which direction is that next line pointing? Up. If I asked you to provide the most stable chair conformation for cis 1,2 dimethyl cyclohexane, this ends up being one of the most common answers, and it also happens to be wrong. So you have to keep in mind that you have to name the structure. To help you with that, draw it as a normal overhead view first, then convert the overhead view into the chair. Okay? So we got a couple minutes. Go through and work on these. If you got questions, raise your hand. I'll come to you.